So section 5.1 is on exponents, and I've already had some people tell me, oh, these are really easy, and but for some of us it's not, and for a lot of people we think it's easy because we were given a set of rules, and it was kind of like memorize these, get your answer, and go. But then you don't do it for 2 weeks and you forget. So the rules I'm going to argue are not enough. You really should understand. But we're going to start with the basic thing. When I have an exponent, there's two parts. The b is the base, so I have b raised to the e. The e is the exponent, okay? The base is the number we are multiplying by. The e, the exponent, is the number of times we multiply by that base. So for instance, here I have 3 to the, I'm going to change that to 3 to the 4th, okay? So 3 to the 4th, what that means is multiply by the base, multiply by 3, how many times? This does not mean 3 times 4. We already have something for that. It's called 3 times 4. Literally what this means is multiply by that base, multiply by that 3, 4 times. We multiply by the 3, 4 times, right? And so then we could multiply that. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So 3 to the 4th power is not 12, it's 81. Okay? Some of you would have done these two to make a 9, these two to make a 9, and 9 times 9 is 81. I'm fine with that as well. Okay, let's keep going. So what if I have a to the 3rd times a squared? Some of you think you know. You're like, say what do you think it is? Some are like, I don't know, a to the 5th, a to the 6th, a to the 1st. A lot of people make it a to the 9th. I get lots of answers for this, but what's right? Well, I have no doubt, because I had a really good algebra teacher. What my teacher taught me was, when in doubt, if you have any doubt at all, write out what it means. What does a to the 3rd mean? We are multiplying by the base, which is a, 3 times. This is a to the 3rd, isn't it? Times another a squared. If I multiply these 3 a's with these 2 a's, we end up with what? How many a's? 5, 6, 9? See, some of these answers just become nonsense now. Because when you write it out, then I look at this and I go, oh, this is a to the 5th. And you're like, oh, yeah, I remember this rule. Just add the exponents. No, we don't just do anything, right? And the key here is that what are we doing with these 2 a's? We're not really adding. We're multiplying, right? So why do we add the exponents? Because the exponents are how many times we are multiplying. So we are not just adding 2 numbers. We are adding how many of the a's we are multiplying by. So we are not really just, it's not an addition problem. So beware. And some of you still are very happy with me right now. Well, let's keep going, okay? So 2 to the 3rd and 2 to the 8th. You're like, I got this rule now. I'm telling you, don't just have the rule. Understand it. Now, do you have to write out all of them? No. This is the one that if you aren't sure, write it out. Could I write out 2 to the 3rd? That would be what? 3 2's. 2 to the 8th would be another 4, 5, 6, 7, 8 freaking 2's, right? So I've got 3 of them, and 8 more give me what? 2 to the 11th. No doubt in my mind. So when in doubt, write it out. That's annoying because it rhymes, and it stuck with me for many, many years. Okay? Here's one where I will catch some people. 5 to the 3rd times 5 to the 8th times 5. So he's like, I got this. This is 5 to the 11th. Nope. Well, I just added the 3 and the 8. Shouldn't just do anything. What is 5 to the 3rd? 3 5's times 5 to the 8th. 4, 5, 6, 7, 8 friggin' 5's times another 5 at the end. Count the 5's. 3, 4, 5, 6, 7, 8, 9, 10, 11. There's not 11. There are 12. Technically, I could call this 5 to the 1st and add the exponents, but it's not really just adding. It's not an addition problem. You're adding exponents. You're adding the number of times you're multiplying by 5. We are multiplying by 5 a total of 12 times. If I have r plus s to the 7th, r plus s to the 6th, I'm not going to write this one out, right? We write it out when it's easy so that I can handle it and understand it when it's harder. What's our base? What's our group that we're multiplying by this time? And how many times am I multiplying it? 7 times and 6 times would give me a total of 13 times. Could I write that out there? Yes, I could write out r plus s 13 times. But the idea is what? Write it out when it's easy so that when I get to something harder, I don't have to go, what's the rule? The same rule that makes sense up here makes sense down here. Okay? In all honesty, the adding is probably the only rule that I really kind of like. The idea of subtracting, drives me crazy. Because you subtract and soon you got to deal with negatives, it gets all crazy. Here's what I do. I have a to the 5th over a to the 3rd. I know that a divided by a would cancel out, leaving me with a 1, right? So how many a's are on the top? And by the way, if you have doubt about this, again, write out how many a's are on the top, how many are on the bottom, and start canceling. Every a divided by a becomes a 1, becomes a 1, becomes a 1. So what am I left with? A squared. That, I have no doubt. You write it out, you do it. Some of you are like, oh yeah, it's just 5 minus 3. Awesome. Do this one, a to the 3rd over a to the 5th. If you do a subtraction problem, you're going to end up with a to the negative 2. Which is actually not the way we want the answer anyway. And some of you know how to fix that, and that's fine. But here's all I would do. I would write out on the top 3 a's. And I would write out on the bottom. I got to make some more room here. There we go. I would write out on the bottom 5 a's. Because currently this is not the answer we're looking for, right? And I would start canceling. 1, 1, 1. How many are on the top? 3. How many are on the bottom? 5. Cancel them. What's left? Well, a squared. But here's the problem. Not just what's left. Where is it left? Because the answer is not a squared. That a squared was left on the bottom of the denominator. Well, wait a second. So stick it on the bottom. What goes on top? What's left up there? Some people will say nothing. They all disappeared. No, because anything divided by itself is not nothing. Anything divided by itself would make 1. 1 over a squared, and that's the answer I would want. That's the answer you need to have. Yes, you can use subtraction, make it a negative exponent, and fix it. I would just, and like I said, I don't have to write this out. I can think about how many are on the top, how many are on the bottom, cancel them, and find out what's left and where. For instance, I will write this out, and some of you may need to because maybe you still have some doubt. But I would look at this and go, right, how many 7s are there? 9 on the top, 4 on the bottom. How many in common that would cancel out? 4 of them would cancel, leaving me with 5. 5 where? On the top. If you want to put something on the bottom, you could stick a 1 there. It's not really necessary. Okay? You're like, I don't know, I just like the rule. I'm telling you, it's going to get you in trouble, and I hope you would know by now. I understand you also have a lot of experience, but I have a lot of experience with the math, and I'm telling you, I've worked with students for years that they thought they knew the rules of exponents, and then they get to it and they have doubt. And if you would just take the time and write it out, 5, 6, 7, 8, 9 over 4. And then what? Cancel out. How many are on the top? How many are on the bottom? Cancel, leaving us with 5 on the top. There's no doubt in my mind. I can go straight from this to this, but it's not by using any rules. I'm doing this in my head. And some of you are too, and that doesn't bother me, but I'm telling you, until you can do that in your head, you should not be applying any rules. This should make sense. You get to Math 51, you're going to be doing this with some crazy, crazy rules and some crazy numbers. And people start shutting down and going, this is too hard. The rules aren't working for me anymore. So it should make sense right now when it's easy, so that when we get to where it's harder, you will be able to do those as well. What do I do when it's a mixture of things? Well, I could write it all out. Here's what I would do. Take the 4 over 6. Reduce it. 4 and 6 are both divisible by. So I know my answer is going to start with a 2 on the top and a 3 on the bottom. So basically reduce the numbers. Now cancel the variables. We have 5p's on the top, 2 on the bottom. I see 2 canceling out, leaving me with p to the 3rd on the top. Q to the 7th over q. I see 7 q's on the top, 1 on the bottom. So when they cancel, I'm left with 6 on the top. If that didn't make sense to you, then I would do this. Take the 2/3 and write out. And then write out 1, 2, 3, 4, 5, 6, 7. And 1 cancels, leaving us with 6. You're like, well, that takes too long. I understand. I understand it takes time. But what always drives me crazy is I will watch people try to use rules and save time and then miss questions. And they miss so many questions that they fail a test. And I go, well, you haven't really saved yourself any time because now you have to retake the course. That makes no sense to me. And then I finally convince those people to write them out, and they start writing them out, and they start making sense. They start getting the right answer. If you have any doubt on any of these rules, you should always be able to write them out. 3x squared y to the 5th, 27x to the 9th y to the 5th. Let's start with the numbers. 3, 27. Those are reducible, divisible by 3. Makes that on the top 1 over 9. Talk about the x's. Currently on the top I see 2 x's. On the bottom I see 9. Once again, I'm doing this in my head. 2 cancel, leaving me with 7. Where? Don't put x to the 7th up here. Like, oh no, I had to put x to the negative 7th. What? I mean, it's right, but that's not what we want. Really, where are those x's left? On the bottom. What about y to the 5th and y to the 5th? Somebody's going to apply the rule and they're going to put y to the 0. Technically, it's not wrong, but that would not be full credit. But think about it. What do I have? I have 5 y's on the top. I've got 5 y's on the bottom. They all cancel out. So where do I leave y's? They're all gone. This is the answer we're looking for. All the y's completely canceled out. Not that they disappeared, they just made a whole bunch of 1s. This brings up two things. It brings up a 0 exponent, and it also brings up negative exponents, and so I want to talk about those real quick. I know that 3 to the 1st is 3. I also know that 3 squared is what? Well, 3 times 3, or 9. 3 to the 3rd is 3 times 3 times 3, or 27. What's going on up here, right? As I am adding 1 to an exponent, we are multiplying by another 3. As we add exponents, we multiply by another one of the base. Every 1 we add to the top means I multiply by another 3 down here. That shouldn't be profound. What about this, though? What if I want to go backwards? 3, 2, 1, 0. See, going to the left, we're not adding 1, we are subtracting 1. How do I go from 27 back to 9? It's not by multiplying by 3, is it? We're going the opposite direction. So if adding 1 means multiply by 3, minus 1 means divide by 3. Divide by 3. So how do I go from 3 to the 1 to 3 to the 0? The most common mistake is that people here will tell me that this is 0. And that's incorrect. Because going to the right, we are multiplying by 3, multiply by 3, multiply by 3. Going to the left, we are dividing. So 27, 9, 3. What is 3 divided by 3? 3 to the 0 power is 1. What's 3 to the negative 1? What if I go back one more? Well, then I'm going to divide by another 3. What's 1 divided by 3? Besides kind of a scary decimal, let's just call it 1/3. What if I divide 1/3 by 3? It becomes 1/9. As we go to the right, we are multiplying by 3. As we go to the left, we are dividing by 3. Positive exponents mean multiply by the base. Negative exponents mean divide by the base. So this works for 3. 3 to the 0 is 1. Does this work for any number? Yim? Well, let's see. X stands for any number, right? X to the first is just x. X squared means x to the third means, what are we doing as we add 1? We are multiplying by another, shouldn't use that for multiply. We are multiplying by another x. We are multiplying by another x as we go to the right. So what if I want to go to the left? Instead of multiplying by x, we divide by an x. We divide it away. We divide it away. X to the third divided by x, 1 cancels, leaving me with x squared. X squared divided by x, 1 cancels. Going to the left. What is x divided by x? What about negative 1? What about negative 2? Take that, going to the left, and divide it by x. Makes it 1 divided by x. The next one would be 1 divided by x twice, or 1 divided by x squared. This is a big deal, because this means if it works for x, that it works for any number. X stands for any real number. 0 is kind of an exception with this. We're not trying to get caught up in that. But x, right, we're assuming x is some number, 1 or higher, decimals even. Anything but 0, basically. But anything that is raised to the 0 power equals what? 1. X to the 0 equals 1, which means that any number raised to the 0 power is 1. What about 3 to the negative third? Do not make that negative 9. That's not what an exponent means, right? Positive exponent means multiply by the base. So a negative exponent means the opposite. Instead of multiplying by the base, we are dividing by the base. So what is x to the negative 1? It literally means take 1 and divide it by x. And some of you are like, oh yeah, I remember that. This travels down and the exponent just magically becomes positive, and I did that and I got my gold star. And that's fine, but it should make sense. If a positive exponent means multiply, then a negative exponent is the opposite. It means divide. So let's do a quick recap with this, and I think we're almost done with this section. Yeah. What is 1,948 raised to the 0? Well, anything to the 0 power is 1, including a really big number like 1,948. What about negative 9? What is negative 9 to the 0? Well, it's still a number raised to the 0. It's still 1. What about negative 9 to the 0? Geez, that sounds a lot like what we just said, but it's actually different. See, on the last one, this entire group is being raised to the 0 power. That makes the whole thing 1. On example 11, what's being raised to the 0 power is just the 9. Why does that work? PEMDAS, parentheses, exponent, multiply, divide, add, subtract. See, this 0 is an exponent, right here, right? And the only thing that comes before exponents is parentheses, which is why in example 10, the whole group is being raised to the 0 power. In example 11, only the 9 is being raised to the 0 power. What's that negative doing, really? When I have a negative in front of a number, actually it's multiplying. That's like negative 1 times 9. Okay? So since it's multiplying, the 9 to the 0 becomes a 1, The negative makes it a -1. See if we can do that with here. What's 3x to the 0? Well, the whole group raised to the 0 power would make a 1. What is 3x to the 0? Geez, that sounds like what I just said, right? But it's different. Why? This time, it's 3 times x to the 0. So what's being raised to the 0 is just the x. PEMDAS, the exponent occurs before the multiplying. So this really becomes 3 times 1, or just 3. What's 7 squared to the 4th? You're like, oh, I remember there's a rule for this. Somebody's going to tell me 7 to the 6th. Somebody's going to tell me 7 to the 8th. Somebody's going to tell me 7 to the 16th. I'll give you a hint. If you have any doubt, write it out. What does 7 squared mean? Now that group is being raised to the 4th power, which means that 7 squared is occurring 4 times. When I look at all that, I'm multiplying all those 7s together. You tell me, are there 6? Are there 8? Are there 16? See, some of those answers just become ridiculous. The minute you write it out, you go, geez, that just looks like there's 8 of them. Well, guess what? There's 8 of them. I wouldn't write it out to this point because I don't need to. That first rule, like I said, the adding exponents, if you're really comfortable with that, and most people are, then all I would do to make this make sense is I would just do what's 7 squared to the 4th. Well, that's 7 to the 2, 4, 6, 8. That's what I would do. But if you're like, and I don't feel as comfortable with that, I have a little more doubt than you do, Mr. Akers. Okay, then write it out. Write out as much as you need, not to get the answer right because I just memorized the rule, but to get it right because it makes sense. What's y to the 5th to the 3rd? Try it out. Take a second, pause these. See if you can just do these with the rule. If you can, then chances are you actually understand what you're doing and you're not just applying the rules. I'm going to go ahead and start on this one. Y to the 5th to the 3rd. What would I write? Y to the 5th to the 3rd, which means 3 times. Now, for me, this next rule makes complete sense. If I look at this, 5y's, 5y's, and 5y's, it's y to the 15. If that doesn't make sense, then I literally could write out y to the 5th and write that out, what? 3 times, and end up with y to the 15th. People are looking at me like I'm crazy because they're like, that's not necessary. It's so much more complicated. I'm telling you, I've worked with enough students that if you're not comfortable with the rules, if they don't make sense, you should be writing these out till these rules make sense. This is not something you should have to memorize. This is something that should make sense. What's 3a to the 3rd? I'll tell you right now, 27a to the 3rd. I didn't do that using rules. In my mind, when I'm actually doing this, I see 3a to the 3rd and I'm thinking 3a times itself 3 times. Then I multiply 3 times 3 times 3 is 27. A times A times A is a to the 3rd. I'm not using the rules. I'm writing it out. Now I'm able to do it in my head and kind of make sense out of it. Yes, I know the rules and I could apply the rules, but I don't. They're not on this. Heck no. This should make sense. It needs to make sense when it's easy, so you can apply it, the same rules, when it's harder. What's negative 5x 4th squared? Some people will tell me negative 10 x to the 8th. Some people will tell me negative 10x to the 6th. I'll have some people tell me 10x to the 8th, 10x to the 6th. I'll have some people tell me 10x to the 16th, negative 10x to the 16th, 25x to the 16th, negative 25. I've seen all these answers. Are they all right? They can't all be right. what do? Write out -5 x to the 4th squared. That means I write that out twice. What is -5 times -5? Like, I thought I was supposed to add sometime. No, you're not understanding then. We were never really adding. We were multiplying. When you are adding exponents, you're adding the number of times you multiply. You're confusing yourself. Write it out. -5 times -5 is positive 25. X to the 4th and x to the 4th is x to the 8th. I'm not really adding there. What am I doing? I'm adding how many times we are multiplying, but we're really multiplying by x 8 times. This example here, I can tell you the answer right off the top of my head. It's not math magic. I know these rules. I understand these rules. C, can you do this? Just apply all your rules and knock this out. You should have 18, a to the, looks like 17th, b to the 6th. How did I do that? I did this. 3, a to the 7th, b. 3, a to the 7th, b. That's 3, a to the 7th squared. Twice. 2, a to the 3rd, b to the 4th. And then I could multiply 3 times 3 times 2. 9 times 2 is 18. A to the 7th, a to the 14th, a to the 17th. b squared to the 6th. If I lost you on that last part, then guess what? Write it out more. And you're like, but it takes forever. It doesn't matter if it helps you get it right. If it helps you get it right and it helps it make sense, that's more important than saving yourself 20 seconds. 3, 9, 18. Count the A's. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Count the B's. 1, 2, 3, 4, 5, 6. No doubt in my mind, because I haven't memorized these rules. I get them. They make sense. What about fractions? If you're not sure if that bottom number is supposed to be a 5 or a 10, write it out. What's x over 5 squared mean? Times. How do I multiply fractions? Straight across x times x is x. 5 times 5 is 20. 3a to the 4th over b to the 3rd, all cubed. Oh boy. What do? Write it out. 3a to the 4th, b cubed. 3a to the 4th, b cubed. 3a to the 4th, b cubed. Do I do this every time? Not on paper. I've done this enough that it makes sense. I can do this in my head. 3 times 3 times 3 is 27. A to the 12th, b to the 9th. If you need more, then write out more. 3a to the 4th, b cubed. 3a to the 4th, b cubed. 3a to the 4th, b cubed. 27, 4, 8, 12 a's, 3, 6, 9 b's. No doubt in my mind. Write it out. I'm going to leave this here for a second. Yeah, there we go. So this is kind of all of our rules, but I'm telling you, and copy it down, have this in your notes. But this is not something you should have to memorize. All of these rules should make sense. Our product rule, a to the m times a to the n, yes, I can add the exponents. Does that make it an addition problem? No. We are multiplying, which means we are adding the exponents. We are adding the number of times we multiply by that base. Quotient rule, I hate this rule because it just jacks the people if you don't understand it. Yes, I can subtract them. I don't like to. I like to write it out, cancel, see what's left. I'm not lying, that's how I do these. Power rule, yes, I can take the exponents and I can multiply them. People get themselves in trouble with this, so what do? I'd write it out. AB to the n, that n distributes like magic. No, write out AB times AB. Well, n times. Yeah, I know, it's kind of complicated, but basically each thing gets raised to the nth power. Fraction, each term gets raised to the nth power. I wouldn't be using these rules, not in this course. Now you get to my Math 51, I'm going to be telling you, you need to know these rules. And you should have had a good Math 55 teacher that made you write it out so you understood it, so that now that you're in Math 51, we're going to apply it to some crazy stuff. Also, anything raised to the 0 power is 1. Anything to the first power is itself. And we're going to leave it at that. I'll pick up with that on the next section. So this is where we left off in the first section. I'm going to go ahead and just scoot this down and move into the next section. You should already have this in your notes. Talk about negative exponents. We already saw this kind of in the last section. I just can't stand teaching the first without us dealing with negative exponents. But what does a negative exponent mean? Well, if a positive exponent means multiply, then a negative exponent means divide. So a to the negative n, we bring it down, and it means 1 divided by a to the n. Instead of multiplying by a to the n, we are dividing by a n times. So a to the negative fifth does not mean a times itself 5 times. It means take this, move it down, and instead of multiplying by a 5 times, we are going to divide by a 5 times. Notice it does not make that a negative. That doesn't all of a sudden become a negative. That's not what a negative exponent means. We already got something that means that. That's a negative in front. That makes things negative. A negative exponent means instead of multiplying by m 3 times, bring it down, and we are dividing by m 3 times. What about this? 3x squared y to the 4th. Where's the negative exponent? Does everything move? No. What has the negative exponent? This is 3 times, 3 is positive exponent, x squared is a positive exponent. Leave those alone. Take the y to the 4th down. That negative exponent on the y leaves the 3x squared on the top and moves the y to the 4th on the bottom. What about 3x to the negative 2? Come on, there we go. A lot of people will make that 1 over. Because this is really what? 3 times x to the negative 2. And this exponent occurs first, and so it only occurs to the x. And so what we're left with is a 3 on the top and the x squared on the bottom. What about if it's on the bottom? 1 over x to the negative 2. We've actually done this before. It's not a very difficult kind of rule, but here's the idea. How do I divide by a fraction? Well, we don't. We multiply by the reciprocal. So this ends up flipping back up, and we end up with x to the positive 2. Okay? Dividing by a fraction is like multiplying by the reciprocal. We flip it, and it changes from dividing, negative exponent, to multiplying, positive exponent. If I have 3 over x to the negative 2, does the whole thing just flip? Where's the negative exponent? Only on the x. So that 3 stays, and then the x moves up next to it. So what is t to the 5th times t to the negative 2? By the way, there's a rule for this. I can take those exponents and add them. 5 plus negative 2, t to the 3rd. I'm not a huge fan of the rules, so here's what I would do. Take the negative exponent, bring it down. What's left on the top? What's left on the bottom? Now I could apply the quotient rule. I could cancel. 5t's on top, 2 on the bottom, cancel out, leaving me with 3 on the top. If that still doesn't make sense, I could write out 5 on the top, 2 on the bottom, canceling leaves me with 3 on the top. Write out as much as you need to get it right, to get it to make sense. What about this one? Well, I gotta try to apply the quotient rule, negative 4 minus negative 5. It's just not worth it. The one on the top moves down. The one on the bottom also has a negative exponent. It moves up. So what's on the top now is x to the positive 5 On the bottom, x to the positive 4. I'm still not applying any rules. I'm canceling. 5x's on top, cancel with 4x's on the bottom, leaving us with 1x on the top. 5x squared y to the third raised to the negative fourth. You can apply a rule to this. I wouldn't. I would deal with the negative exponent first, which means what would move? Would be the y. So I've got 5x squared over y to the third, all raised to the fourth. Don't apply a rule to this. A lot of people are going to tell me that this is 20. That's a lie. It's a damn lie, right? I thought we multiplied the rule here. Don't do it. Write this out. 5x squared, y to the third, 5x squared, y to the third, 5x squared, y to the third, 5x squared, y to the third. Why am I doing this? Because 5 times 5 times 5 times 5 is not 20. 5 times 5 is 25, times 5 is 125, times 5 is 625. X squared, x squared, x squared, x squared. Write out as much as you need to. We should know by now that is how many x's? It's like 8. On the bottom, y to the third, y third, y third, y third. We should know by now, or write it out if you're not sure. How many y's is that? 3, 6, 9, y to the 12th. I can go straight to this answer. Not by any math magic. I can just do all these steps in my head. I'm not cheating. I'm not like applying some magic rule that I've not taught you. This is how I actually do these. And I'm telling you from my experience, when you start writing it out and making sense, people start being more successful. Onward. What do I do here? What moves? Well, I see a negative exponent on the x, so that sucker's going to move down. Does this y move? Does this y have a negative exponent? Leave it alone. Does this x squared move? Does this y to the fifth move? Nothing else moves except that x to the negative third. So you're like, wait a second, what about this? Does that move? No, that's not a negative exponent. That's a negative number. That's different. Negative numbers are just negative numbers. That's negative 10. We don't all of a sudden start flipping every time we see a negative number. Only a negative exponent. So what do? Well, let's go ahead and take the negative 10 over 5 and let's divide it. Negative 10 divided by 5 is negative 2. You could also have thought of it by reducing top and bottom by 5. Would give me negative 2 over 1 if you want. On the bottom, we now have an x squared and an x to the third. I'm going to apply a rule for that. I'm going to make sure it makes sense to me. I'm left with a y on the top, 5 on the bottom. Start with the x's. X squared, x to the third. If I wrote those out, multiplied them together, I would have a total of 5 x's. If that doesn't make sense, write it out. That's not 6, it's not 8, it's not 9. You'd be surprised the answers I get. The y's, when I cancel, 1 y on the top with 5 on the bottom, only one in common that cancels, leaves us with 4. Where? The y's are left on the bottom. Don't apply a rule where you end up having to deal with a negative exponent. That's nonsense. This should make sense. 1 over 5 of them, 1 cancels, leaving us with 4. Okay? Almost done here at the end here. How do I deal with a fraction and a negative exponent? This, I think, is a better argument. How do I divide by a fraction? Right? We don't. When I divide by a fraction, we multiply, positive exponent, by the reciprocal. So a over b becomes b over a. How do I divide by a fraction? We multiply by the reciprocal. It flips, and the exponent becomes positive. So how do I handle x to the fourth over 2y, all raised to the negative third? I want to deal with this negative exponent first. So that means everything that's in here becomes a reciprocal, flips, and instead of dividing, now that exponent is positive. Still need to simplify this. Don't try to do this in your head. I mean, if you're able to get ay to the third over x to the 12th, that's awesome. But you're not really doing any math magic. All you're doing is this. Oh, just 3 of them. And then you're multiplying that in your head. 2 times 2 is 4, times 2 is 8. Y to the third, x to the 4, 8, 12. No magic tricks. This should make sense. For section 5.3, we're going to focus just on specifically scientific notation and that application with the exponents. Just a quick recap of what scientific notation is. We have to remember that the first number must be in the ones place. A lot of people go, oh yeah, between 0 and 9. Well, no. There needs to be something in the ones place. So really it should be between 1 and 9. So between 1 and 9 in the ones place. So 1.8 would be fine because there's a 1 in the ones place. 0.8 would not be fine because there's nothing in the ones place. So the first number must be in the ones place between 1 and 9. The second thing that we do is we take that number, we multiply it by 10 raised to some power. Okay? If that power is positive, then we are multiplying by 10 exponents. If we have a positive exponent, it means to multiply by the base. So as we multiply, the decimal moves to the right. The number grows bigger with a positive exponent. If it has a negative exponent, well, we've talked about this, a negative exponent instead of multiplying means to divide. So if we divide by 10, what that does is it moves the decimal to the left. So this is kind of our recap of what scientific notation needs to look like. Let's go ahead and look at some applications. So here are some numbers that are already in scientific notation. 1.8 times 10 to the 9th. Okay? To turn this back into standard form, or decimal form, we're going to take that 1.8 and we're going to multiply it by 10. 1.8 times 10 would be 18. Times another 10 would be 180. See, as we multiply by 10, this decimal keeps moving to the right. That's what multiplying by 10 does. How many times are we going to do that? Well, 9 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, till the decimal stops. A lot of people go, awesome, so you have 9 zeros. No, that is not true in this situation. There are times where that will be true, but that is not a good rule. Move the decimal that many times, so this time there are 8 zeros. 3, 6, 7, 8. Okay, 2.3 times 10 to the negative 4. I'm going to do the same thing. I'm going to take that 2.3, but this time the exponent is negative. So instead of multiplying by 10, we're dividing by 10. 2.3 divided by 10 would be 0.23. See, now we're dividing by 10, which makes the number not get bigger, but get smaller. How many times are we dividing by 10? 4 times. Means if I divide it once, it moves once, a second, a third, and a fourth time. So here's where the decimal ends up. So keep in mind, once again, not that many zeros. It'll have 3 zeros to fill it in, so that we have, and I'm fine with this answer, but if you prefer 0.00023, that would be fine. So these are in standard or decimal form. Everything on the left here is in scientific notation. If we can go from scientific notation to standard form, we should be able to go from standard form to scientific notation. Okay? What we're going to do is, once again, go through the rules. The first number needs to be between 1 and 9. So going through this number, the first number that I see between 1 and 9 is the 1. That tells me where my decimal is going to be, 1.53. So when I write this in scientific notation, I'm going to take the first number between 1 and 9, and that will end up in the ones place. What's the second part of scientific notation? Well, it will be times 10 to a, well, how many times does the decimal need to move from here all the way over to where I want it for scientific notation? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And here's where I always catch people, and I don't really understand this. I understand it's backwards from what we did before, but is that 11 going to be positive or negative? Well, A lot of people go, well, we just moved it left, so it needs to be negative. And I go, well, this says take 1.53 and divide by 10 11 times. Will that make it bigger or smaller? See, that makes it smaller. I want it to get bigger, which means that exponent needs to be a positive 11. How do I know that these are equal to each other? Because if I took this 1.53 and I multiplied it by 10 11 times, it would end up turning back into the number we started with. Okay? 9,547.3. What is the first number between 1 and 9? How about the 9? So we're looking at 9 point. Now we're going to put the 5473, but we probably, when I do scientific notation, would round this off some points. So maybe like 9.5 or 9.55 or 9.54, 47. The idea is a lot of time the point of scientific notation is to make the numbers smaller than what we started with. Okay, so we do round these off a lot. It'll once again be times 10. And how many times does the decimal need to move? 1, 2, 3 jumps. Positive or negative? Well, I want these numbers to get bigger or get smaller. So bigger means the exponent stays positive. So, like I said, it wouldn't bother me if we rounded these to 2 decimal places. I'm not sure what the homework's going to do with that, but this wouldn't bother me because that's really the purpose of scientific notation. We got scientists that deal with really big numbers and really small numbers, and we are finding a smaller way of writing those numbers, kind of an easier way of operating with those large and really small numbers. Now this 0.00005842. Okay. What is our first number between 1 and 9? This is where a lot of people would put 0.5. Don't do that. I need to start at the 5. So this is actually where our decimal needs to be. So my scientific notation is going to be 5.842. That's going to get me some credit on the test, right? Scientific notation, we have times 10 to some exponent. Well, how many times did the decimal move from here to here? 1, 2, 3, 4, 5, 6 times. Now this should be uncomfortable for you. These are not the same. Because 5.842, to turn it back into this, we would need to make the number smaller. We would not need to multiply by 10. We need to divide by 10, which means it will be a negative exponent. And check it. If I took 5.842 and moved that decimal back 3, 4, 5, 6 times, do I end up with what I started with? And last but not least here with this example, if I have 6.1134, my first number right there is already in the ones place. That's weird. So we could put 6.1134 times 10 to the, how many times do we need to move the decimal place? 0. This would be something that might show up in the homework. I'm not trying to trick you guys. I wouldn't be doing this on the test. But technically that would be putting that number in scientific notation. I wouldn't need to move the decimal place, so that exponent would be 0. Last but not least here, let's show a couple applications. Why are we having this? Well, because sometimes I'm going to multiply really big numbers and really small numbers, and you're going to have access to your calculator. And I'm going to show you how I would use the calculator with this. But basically, when I'm multiplying this, I would rather not have to do 1, 8 with 1, 2, 3, 4, 5, 6, 7, 8 times. Now you can do that and then put your answer in scientific notation. Or what I would do is I would multiply the 1.8 with the 2.3. What is 1.8 times 2.3? I could even do that without a calculator. Four, 1, 4. So we have 4.14, and then I have times 10 to the 9th times 10 to the 4th. I can use our exponent rules and make that 10 to the 5th. So I was able to multiply those two numbers pretty quickly. without a calculator. And so that's one of the benefits of this. I'm going to double check 1.8 times 2.3. 1.8 times 2.3. 4.14 times 10 to the 5th. Like I said, I could double check. And 0.00023. And that would be 4.14 times 10 to the 3/4. So what we got? Pretty snazzy. Last but not least, and this one's a little weirder, and I wouldn't write it like this either, but basically we can multiply and we can divide them. I would rather think of this as 7.2 times 10 to the negative 7, all divided by 8 times 10 to the 6th. Once again, why would I ever want to do this? Well, you're going to be dealing with multiplying really big and really small numbers in the sciences, right? So I could divide 7.2 by 8. In fact, I could do that without a calculator even. And so these two divide to give me 0.9 times 10 to the... Now these don't match up, so what I'd need to do is I would need to do negative 7, bring up the 6. So it would be 10 to the negative 7, 10 to the negative 6, combines to make 10 to the negative 13. Okay? This is not our final answer, so just be careful with that. And like I said, you're going to have access to the technology. I'm just showing you how I could do this without the technology. But we need to write this because this is not scientific notation. We cannot have that 0 in the front. So if you're real clever, you could make this 9 times 10 to the, what would it need to do? Negative 12, I think. Okay. What I think most people would be more successful with is to put this back in decimal form, which means I'm going to move that decimal back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But I think I might have done it wrong, huh? And then when I want to turn it back into this, I want to know how many times to move it over here, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, see, this was supposed to be a 14. What would I probably do with this? I would take 7.2 and divide it by 8. And this is what I would do if I were you. 7.2 divided by 8. Get the 0.9. And then take 10 to the, what was it, negative 7. Divided by 10 to the 6th. That's not fun. 0.9 times that mess. 9e negative 14. Now this doesn't bother me. See, my calculator just did a lot of heavy lifting for me. But you need to, if you write 9e to the negative 14, the best you're getting is half credit. So we're going to see these numbers in statistics, and we don't write 9e. What that e means is it stands for times 10 to the. So this literally says 9 times 10 raised to the negative 14. That is what that means. 9 times 10 to the negative 14. So please feel free to use your calculator, but if you put 9e negative 14, I will not be giving you full credit for that. You need to write that in scientific notation. So section 5.4 should be mostly a review on adding and subtracting polynomials. We're going to get a little deeper into some terminology on it, but here's the main idea. I can add 3x plus 2x. Those are like terms. The 3 and the 2 combine to give us 5x. I cannot add 3x plus 2x squared. The issue here is that this 3x is just a 3 and an x, and the 2x squared is a 2 and 2x's. So they're not really the same because they don't have the same exponent. technically they do have the same variable, which is important, but they also need to have the same exponent. So 3x plus 2x squared, we would say, is already simplified. Okay, so let's go through a couple examples here. Here I have 9x to the 6th minus 14x to the 6th plus x to the 6th. They are all the same variable. They're all x's, and they have the same exponent. They have the same amount of x's. So we can combine the coefficients. I can combine 9 minus 14 plus, what's the coefficient here, right? If there is no number, that is like a 1, x to the 6th. So I really have 9 minus 14 plus 1. That's negative 5 plus 1, negative 4. We combine the coefficients, and the exponent, x to the 6th, stays the same. We're not multiplying, so we're not multiplying the x's together. We are just combining x to the 6ths. X to the 6th plus x to the 6th give us more x to the 6ths. Okay. R squared plus 3r plus 5r squared. What are my like terms here? Well, same exponent, same power. This one has the exponent but not the power, so it is not a like term. The r squared and 5r squared would combine to give us 6r squared. Remember, if there's no number, it's a 1 here, plus 3r, and that would be completely simplified. 8t plus 6w. We're looking at this and wanting to combine them. Please do not make this 14 of anything. Why not? This has a t, this has a w. They have the same exponent, but they are not the same variable. So this would be already simplified. We can add x's to x's, apples to apples, but not t's to w's. They need to be the same variable for us to combine them. Kicking it up a notch. 9pq plus 3pq minus 2pq squared. Well, these all have pq's, but for them to be like terms, they have to have the same and the same exponent. This squared makes this one not like the other ones. So when I go to combine this 9 and 3 gives us 12pq minus 2pq squared. Remember, the issue is that the 12 is 12, a p and a q, and this is 2pqq, not like terms, so don't combine those. And then we have x plus 1/2 of x. People are like, oh no, we can't do this. Yes, we can. They are both x's, they're both like terms. We can do 1 plus 1/2. So what is 1 plus 1/2? Well, make 1 and 2 a fraction. 1 over 1, give them a common denominator. 2 over 2 plus 1 over 2 is 3 over 2. So I would accept 3 over 2x, or if you divide the 2 in there, you could get 1 and 1/2 x. By the way, that should make sense, that 1x plus half an x gives us 1.5 x. Do not change the exponent, just combine the coefficients. And last but not least, just to see how you are in combining your like terms, I think this is really the scariest thing in this section, and is really not that bad. But 6p to the 4th minus 8p cubed plus 2p minus 1, okay? Minusing a group, what that negative does is it distributes across every term inside the group. So that becomes a plus 7p to the 4th, a minus 6p squared, and a plus 12. This one, since it's adding, doesn't really change much. Alright, so let's start with our highest degree. The highest degree I see is p to the 4th. So we're going to combine all the p to the 4ths. What do we get here? 6 plus 7 is 13. 13 plus 1, 14, p to the 4th. The next highest degree we see is p to the 3rd. There's only one of those, so it will not combine with any more. Bring it down. Minus 8, p p to the third. The next highest degree is p squared. I see a minus 6p squared. Are there any others? Then just bring it down. My next highest degree is p to the first. There are two of those, so they would combine to make 2 minus 3 would be negative 1 or negative p. And last but not least, my constants, negative 1 plus 12 plus 8 should give us 19. If you got that, then you should be ready for the next section of notes. Get to work. So for section 5.5, we're going to be multiplying different polynomials together. I'm going to start off with what should be a review of just multiplying, and then we're going to expand it to multiplying polynomials. But if we had 5x times 6x, we should be comfortable with the rules that 5 times 6 would multiply. So we multiply what? The 5 with the 6 and get 30. And then x times x is x squared. Notice here we're not adding them, we are multiplying, so we use the rules for multiplying. Next one, I have the negative 2 times 3. Those would multiply to give us negative 6. X times x squared would multiply to give us x to the third. And y times y would be y squared. Like I said, these rules should be a review at this point because we've had a previous section going over all the laws of exponents here. 7 times negative 4 would give us negative 28. We're multiplying, right? X to the fifth times x to the third is x to the eighth. When we multiply those, we add the exponents, which means we add the number of times we multiply x. We should have already written all this out to see why when I multiply these together, I end up with 8 x's multiplied. Okay? But we are still multiplying. We multiply the numbers, and when I multiply the x's, we add the exponents. What about that y? Right? There's no other y with it, so we bring it over. So that's kind of a quick review of our rules for multiplying. Now we're going to kick it up a notch. What if I have x times x plus 3? Well, we're going to do what's called distributing. That's where we multiply a term across a group. We multiply a group across a group. Okay? So we're going to take this x and we're going to multiply it across the x and the 3. Why can we just do that? Well, I don't know. Let's see. Here I have some numbers that I have 5 times 5 plus 3. Can I do that distributing 5 and have it still give me the right answer? Well, you're like, well, I wouldn't need to. I could add the 5 and the 3. Okay, so you're telling me that this is just 5 times 8, or this is just 40, right? What if I had distributed? Would it change the answer? What if I had done 5 times 5 and got 25? 5 times 3 plus 15. What's 25 plus 15? We end up with the same answer. So when I have to distribute, like in this example, then it's good to know that when I don't have to, either way I get the same answer. So I can take this x and I can distribute it. X times x is x squared plus x times 3 would be 3x. Do not combine those. Those are not like terms. That would be it. Just distributing that x. Kick it up a notch. If I take this 2x squared and I distribute it, now what's it going to do? I'm taking this entire group and I'm multiplying it by 2x squared. Means that 2x squared multiplies across each term, across all the adding and subtracting. So 2x squared times x to the third, 2 times a 1, so remember there's an implied 1 there, would give me 2. X squared and x to the third should be x to the fifth, minus 2 times 7. X squared multiplies to give me x to the fourth. 2 times 10 gives us 20. X squared times x, I end up with 3 of them, and 2 times 4, negative 8, and there's just an x squared. So that term multiplies across everything in the entire second group. What happens when I have more than one term? Well, it's still distributing, but it changes it a little bit. We take everything in the first group and multiply it across everything in the second group, okay? So basically, I distribute each term in the first group. I take that x first and I distribute it to both terms. And then I'll take the second term, the 5, and distribute it across both terms. I start with x times x, which is x squared, x times 4, which is 4x, 5 times x, which is 5x, and 5 times 4, which is 20. Notice what did we just do there, right? We applied the rules of multiplying. We are multiplying in this section here. So we're doing the rules of multiplying. Don't make this 5 and 4 into a 9. That's utter nonsense. We were multiplying there. Okay? We multiply everything in the first group across everything in the second. Second, we look for any like terms. This can be simplified. Those two in the middle are like terms. So I end up with x squared plus 4 and 5 add to make 9. The x, since we are adding here, stays an x. Differentiate when I'm multiplying, use those rules. When I'm adding and subtracting, use those rules. They are a different set of rules. And this would be it. We cannot combine the x squared and the 9x. They are not like terms. Let's keep going. 4x minus 3 times x minus 2 here. We start with the 4x times x, gives us 4x times negative 2, gives us 4 times negative 2. Negative 3 times x gives us, and negative 3 times negative 2 is a positive 6. Combining like terms, we have 4x squared minus 11x plus 6. How did we get that negative 11? We combine negative 8 plus negative 3 to get negative 11 using rules of adding. Okay. I do want to show you the area model, and this is something that if you're not comfortable with the algebraic way of approaching it, this makes it a little more visual. It does become somewhat impractical when they get a little crazy, but it has some really cool applications in Chapter 6, so I do want to go over it. So what you do is you take basically the first group, okay, we're going to take this first group, and we set it on one side, 4x minus 3, so it's separated into two sections. And then we take the x minus 2, and we put it in its own section. But notice it's also separated, two terms and two terms. And then I can find the area of each of these by multiplying. 4x times x is 4x squared. This little rectangle right here would be x by negative 3. Negative 3 times x is negative 3x. So basically we have distributed that x to both of these terms. Let's do the same thing with the negative 2. Negative 2 times 4x gives us negative 8x, and negative 2 times negative 3 is positive 6. Keep in mind, this is not your answer. Don't leave your answer like this. You do need to combine the negative 3x and the 8x, so these two are like terms. They need to combine. But you also need to make sure you write this in descending order, which means what? The highest power, the x squared, comes first. These two combine to make negative 11x, and then the plus 6. We put it in descending order from the highest degree to the lowest degree, which is no power there, right? Okay. Last one. Show me you can do this, right? Can you distribute? You're like, oh, this is scarier. Well, the rules don't change. The distributing said take everything in the first group and multiply it across everything in the second group. Take this first term and distribute it across everything in that group. 5x to the 4th times x squared gives us 5x to the 6th. 5x to the 4th times 2x gives us 10x to the 5th. That plus sign's going to drive me crazy. All right. And we're done with that first term. Have I done everything in the first group across everything in the second? No. We have a negative 2x squared, so we got to distribute that. Negative 2x squared times x squared gives us negative 2x to the 4th. Negative 2x squared times positive 2x gives us negative 4x to the 3rd. Am I done distributing now? Well, I've done the 5x squared, I've done the negative 2x squared. I have not done the 3x, so we're not done distributing. We need to also take that 3x and multiply it. This is where the little lines get a little crazy, but basically that 3x will also distribute each term. So 3x times x squared gives us 3x to the 3rd plus 3 times 2 is 6x squared. All done? No, keep in mind, if there are any like terms, and there happen to be some right here, you do need to combine them. Put this in descending order, so starting at the highest power, then the next highest exponent, then the next highest exponent, and then those two became negative 4 plus 3. Notice right here, that's not going to become negative 12. That's not going to become x to the 6th. Up here we were multiplying. Down here we are adding, combining to get negative 1 x to the 3rd plus 6x squared. And that's how I would want that. I do also want to show you, because that's a lot to keep track of algebraically. This might be less intimidating if we can make it into an area model. So what you do is you take the 5x to the 4th minus 2x squared plus 3x, three separate terms, so three separate sections of the box. And then the other group was x squared plus 2x, so then I'd put the x squared and the plus 2x right here. What do we do now? Well, we find the area of each of these rectangles. 5x to the 6th, 2x to the 4th, 3x to the 3rd, 10x to the 5th, 4x to the 3rd, and 6x squared. Do not forget to combine, since these are like terms, they'll combine. So writing our answer, that would be 5x to the 6th, 10x to the 5th, putting it in descending order, 2x to the 4th, these combine to make negative 1, x to the 3rd, and plus 6x squared. My answer did not change. If you like the area model, if that's a nice way of organizing it, please do that. I've seen people get through intermediate algebra very successfully with just that skill alone. So I encourage that. Let me also say real quick, I know I had somebody that wanted to take this 5x to the 4th minus 2x squared plus 3x times x squared plus 2x, and they wanted to distribute it all backwards. Let me just tell you right now, this is okay. You can distribute. I can multiply in any order, so I can distribute the first group forward, or I can distribute the second group back. If that irritates you, then don't do it. If that's intimidating, don't do it. But somebody was going, well, I just want to do it that way. Okay, go ahead. That doesn't bother me at all. Do that and verify. You should get the same answer. 5x to the 6th, 2x to the 4th, 3x to the 3rd, minus 4, right? It's all going to turn into the same thing, okay? That's it. So good job. We have one more section.